もしやコスモでは
Cosmo makes me feel.
Cosmo AP Luxury Sports.
Welcome to episode 50 of my 76 Mazda Cosmo Restoration. This is part 4 of the instrument cluster and possibly the most information-packed episode I've ever released. So we're going to start right where we left off last time, and that is designing the control electronics. I'm using CAD to design the circuit and board pattern because CAD can output the Gerber format used by PCBWay and other PC board fab houses, unlike Copper Connection, which cannot. Now, I'm not going to cover every detail of designing this circuit because it is going to be kind of a long and it might be kind of boring process, but I will cover the basic building blocks of it and how each individual section works so that everybody can understand it. Of course, the schematics will be published on my website for those who are interested in a more detailed look. The first part of the circuit is the Atmel 1284 processor and the support components. Up here we have the capacitors needed to decouple the 5-volt power supply connected to the power supply pins. The reset needs to be held high with a 10K resistor to 5 volts. The crystal here with its load capacitors to provide a 16 megahertz clock. The analog reference pin decoupled with another capacitor. And the 6-pin AVR programming header connected to 5 volts, ground, and the SPI bus. That's the minimum stuff needed to run the processor. And in fact, if you look at many Arduino boards, you're going to find a very similar arrangement. Next is the power supply section, which has to provide a clean 12 volts and a very clean 5 volts to run all the electronics. Instead of using the LM7805 linear regulator, I've decided to use an LM2674 switching regulator, which is basically a switching power supply in a chip. Generates a lot less heat and is a lot more efficient. So the circuit for that is right out of the datasheet, basically. An input smoothing capacitor, an output smoothing capacitor, the required inductor and Schottky diode to smooth the output, and of course provide the inductance for the whole switching supply paradigm to work, a feedback connection, and then on the input of that, a MOV to protect from voltage spikes, reverse bias diode in case there are reverse polarity voltage spikes, another diode in case anything gets connected backwards, and that's the power supply. The circuit has two business ends. The first business end takes care of the CANbus communication, and the circuit is basically the same as the commonly available Arduino CANbus modules. It consists of an MCP2515 to SPI CAN controller connected to a TGA1051 CAN transceiver. The MCP2515 connects to the processor via the SPI bus, and there's a 10 kilo ohm resistor to hold the chip select line high so that when I'm programming the processor through the same bus, the MCP2515 doesn't respond and mess up the programming. It needs its own crystal with load capacitors. Its reset line needs to be tied high through a 10 kilo ohm resistor, have a 0.1 microfarad capacitor for input filtering. Then it connects via the transmit and receive lines to the actual CAN line driver, which is responsible for talking out on the CAN bus through the connector, which also provides 12 volts and ground to power the circuit. The 1050 is the common CAN line driver used in the modules, but the 1051 is actually a slightly improved version. Same pin out, same functionality, direct substitution. And of course it has a 0.1 microfarad filtering capacitor. And while I was working down near the connector, an optocoupler is added so that a 12 volt ignition signal coming in on pin number 3 will activate the optocoupler, causing this line to be pulled down to ground, which leads all the way over to pin 7 of port D, So now the circuit can know when the ignition is switched on. Well, now the circuit can start to do something with those inputs, which means adding the stepper motor controllers for the gauges. Now, I don't think that I can make anything more compact than these pre-made little A4988 modules, so that's what I'm using. They're really simple to use. All one has to do is give them power, a connection to the motor, and a connection to the processor with one external component. So the motor controllers, 2 of them, get added to the schematic with an output connector to connect to the motors. They need a 100 microfarad filter capacitor to filter the 12 volt supply for the motors. And then simply 2 lines to the processor that control both direction and tell the motor when to step. Additionally, the reset and sleep lines get tied together to keep the chip enabled all the time. Well, the last device connected to the circuit as the output are the LCD screens, keeping in mind that there are 2 on the speedometer and a Nextion HMI on the gauge to the far right, which I guess will be the everything screen. Replace the 2 useless warning lights. So these displays are actually pretty easy to control because they're just SPI bus devices. So they connect to the same SPI bus as the CAN controller. The only difference is that these devices use 3.3 volt logic. So there has to be a 1K dropping resistor anytime they connect to the output of the Atmel chip. Now, because a screen is just an output device, they only require the 2 SPI lines plus a reset connection, which can be shared between both screens, and the data or command select line, which has to be unique per screen, and the chip select line, part of the SPI bus, again unique per screen. So I ended up using only 5 data pins plus the two SPI pins for the screens. Additionally, I've connected the backlight through a 100 ohm resistor and a P-channel MOSFET tied together at the gates so I can control the backlights of the screen via a data pin on the Atmel. The Nextion screen is pretty awesome. It's just a serial device, so I've given it a connector down here with 2 filtering capacitors connected to one of the serial ports of the Atmel. And also, I took the liberty to add this connector here, which connects to the I2C bus, just because. And it has 2 filtering capacitors on the 2 power supply lines. That could be very useful if maybe I just wanted to put a single I2C screen somewhere, or another I2C device that I haven't thought of that I might add in the future. Now, the final component needed is the rotary encoder. And that simply consists of 2 terminals for the switch, and then 3 terminals, a common, and then a clockwise and counterclockwise signal. For the rotary motion, that's just simply this connector here. I connect one side of the switch and the common to 5 volts. Bring the other side of the switch all the way over here to pin PD4. And filter it with a 0.01 microfarad capacitor so we don't get any bouncing, and hold it to ground with a 10K resistor because there's going to be noise. The signal lines are exactly the same. Each one of them goes to a data port with a resistor and a capacitor. Only difference is that these have to connect to very specific pins on the microcontroller, PD2 and PB2, which resolve to interrupts 0 and 2, because this could be turned at any time by a person and it has to interrupt what the processor is doing in order to process that turn. Oh, and I also corrected a few other mistakes which you may or may not have noticed. I flipped my MOSFETs around, they were backwards, and I swapped the 100 ohm resistor from after the MOSFET to before the MOSFET. That way the voltage is a little bit lower on the drain of the MOSFET, so it should switch off without having to add an external driver transistor. I can connect it directly to the microcontroller. In addition, I also brought the enable lines out from the stepper motor controller to pin on the microcontroller so that I can turn the stepper motor controls on and off. And thus finishes the design of the instrument cluster controller. Now, I have to assign physical packages to all of these components because in electronics, everything seems to come in about 9 different form factors. Once the packages are assigned, I can design the circuit board. So we'll do the packages off camera because it's just a bunch of pointing and clicking, really boring, and then we'll zip through the layout of the circuit board. Now that the schematic is done, it's just a matter of exporting it to a netlist, and then opening the printed circuit board editor and importing that netlist. Which dumps an enormous pile of stuff onto this blank circuit board. Just plop that down right there. Zoom in a bit bigger. And there's my circuit board. So what you're seeing are all of the physical footprints of all of the components I've used, connected by these white lines called the rat's nest, for obvious reasons, that mimic the connections on the schematic. So now it's my job to arrange these things into a somewhat organized board and make all of these connections with traces. And what I like to do is usually just start and move things out into the groups of components that belong together. And I kind of already know, some of this stuff, like the crystal here has to go with the processor, which I already moved down. And these big capacitors here have to go with the stepper motor controllers, one for each. There's an inductor that goes with the power supply. I'll toss that over here. There's the programming header for the processor. It's that near the processor. Okay, so I have a bunch of that to do. You kind of get the idea. Get that done, and then we'll turn the camera back on. Well, now that everything's in place, I can actually start connecting things with traces. So what I like to do is start with the most obviously placed parts first, like for example the crystal. And that needs to be close to the processor, and it needs its 2 capacitors. Kind of just tend to shove them as close to one another as possible. And connect them with traces. I like 9.84 mil traces because honestly they're really small, but they're typically the cheapest traces PCB fabs can do. Now the grounds don't really need to be connected because I'm going to pour a big ground plane, but sometimes I like to connect them just so it gets rid of part of the rat's nest. And another thing that is always near the processor are all these filtering capacitors. Oftentimes this is an exercise of just finding out where the parts want to go. And generally too, gonna have to move things around a little bit once Now the trick is to think a bit ahead with your traces and try to avoid blocking yourself into a corner. This capacitor here could have gone anywhere, but its best spot was right at the crystal, because then I had a straight shot down to the 5 volts, and the ground, well, that'll take care of itself later on. So that's processor and its capacitors. Okay, so I got a bunch more of that to do, and I think you get the idea. The beauty of doing this on the computer is I can work on it anywhere, so I don't have to be sitting in my shop to work on this project. So what I'll probably do is simply work on it throughout the week, etc., when I have some time, and then I'll just revisit it on camera to show you what I did if it turns out to be at all interesting. Well, CAD can be pretty obtuse to learn, but once you know the hotkeys and the shortcuts, you can move pretty quick. I mean, some might even say 2,000 times normal speed. I'm just laying out the traces for the crystal necessary to run the CANbus controller, and some of the filter capacitors there. Since this is a multi-level board, I can start out running my trace along the top, and then when I need to, drop to the bottom right there and continue my trace, then pop back up to the top. Very convenient, no jumper wires. And sometimes I like to zoom in to obscene levels, just so that I can make sure that trace is exactly how I want it. I'm just laying out the power supply area right now, and it's worth mentioning that the placement of these components is really critical because it's a switching power supply. So not only do I have to put them in an area where the high frequency won't necessarily interfere with something else, but the traces have to be very thick to carry the power, and additionally I'm going to have to do a copper pour all over most of this area, which is going to envelop these traces anyway to keep interference down with the rest of the circuit. Because, well, 2 reasons. 1, typically that's what you need in a switching power supply. And 2, the data sheet of the chip was very, very specific. That is what's to be done. Yep, we'll just hug these resistors as planned. Then the real problem is this via, which is in a dumb place. Let's get rid of this. Get rid of that, get rid of that, and this trace here, let's put them via here, connect, much better. Okay, now you have a straight shot over. I don't know why I didn't think of that in the first place. Get rid of that via. Clear all these old tracks out. Get rid of that. Clear these. Okay. Now we have a hot dog in a hallway. Okay, straight across, straight through, and right to the pad. Easy. Okay, bottom layer and straight across. Let's let the auto router thing do its magic. Now see, if I drop to the top layer here, straight across, up and over. Brutal. And about 8 hours later, the board is routed. One final step, which is to pour the ground plane, just a sheet of copper on both sides of the board, which serves as the ground. So all I need to do is draw it out. Let's put that on the, start with the front copper and draw out my zone. You don't want to go right to the edge of the board because some fabrication companies have issues with that. And also when the boards are cut out, it could end up separating the ground plane or shorting it to other layers. And you don't want that. Oop, whoa. And right here. Bang. And that automatically fills the blank area with a copper ground plane. Then let's just duplicate that to the bottom as well. Zones, duplicate onto layer. That would be the bottom. And refill. And the board is done. Obligatory 3D view. Okay, then what I can do is send that out to be manufactured. There's about a 2-week turnaround from China. A little bit longer right now because there seems to be a virus. But in the meantime, I do have a bunch of stuff left to do. I've printed out a copy, and before the board goes out to manufacture, I'm just making sure that all of the component packages I chose on CAD actually fit the components themselves, because during the process of designing the board, I had to make a few substitutions in component choice. That one's going to be close. Of what I designed with versus what was available when I ordered. And yep, everything seems to fit, so the board can go out to be manufactured. Spent some time off camera designing the boards for the stepper motors and the rotary encoder. Since these are only one-off boards, I will just print them myself. Fortunately, this is my last page of toner transfer paper, so I better get this right. Well, I guess I should have printed these side by side instead of one on top of the other. Could have wasted less paper. At this point, my yield on these things is about 100%. You just have to know your laminator. Do you know your laminator? See if you can spot my mistake. See my mistake on the center board? Yep, I accidentally drew the outline on the copper layer, thus shorting all these traces together. Of course, that's why the FSM invented Dremels. And fixed. Now it's just a matter of soldering it all up. Basically, each board gets its component, which in this case is the rotary encoder and a matching connector, in this case a 6th position. Space limitations on the tack means that I have to use a surface mount right angle connector here. So that is best done with a little bit of soldering paste and the hot air solder. Then the motor pins get soldered manually. And off camera, everything got connectors. I just remembered I need turn signals. So off camera, I whipped up another board which uses the same RGB LEDs that I did before for the turn signals. And there's enough flex in this board that it can just screw right in. Perfect. You may or may not be able to see the LEDs just at the bottom of those signal cavities. Well, I just whipped up a very simple test rig using an Arduino Nano, which just blinks each side 3 times and then moves to the next side. So, seems to work. Of course, these being RGB LEDs, they can be any color I want. So let's say I wanted blue signals. Just a simple code change and upload a new program. Now my signals are blue. Of course, I think the turn signal lens in the dash is green, so unless I replace that, I'm stuck with green regardless. Who the hell would want blue turn signals anyway? Had to add a little clearance for the LCD connector. Much better, a little bit more clearance. Now it fits in easier. Trimmed and fitted the other side in the same way, so they're now sitting nice and flat. Time to make some mounting holes. And I think all I'll have to do is just screw these down. Now neither the board nor the gauge cluster is flat, so these just screw in very lightly. Then during final assembly, what I'll do is I'll put some thin foam between the backlight board and the cluster, just for some extra padding and to take up the undulations in the shape. And I don't know what happened. As I was looking the other way, another hole appeared. I mean, obviously I didn't drill the hole in the wrong spot the first time. Now each one of these boards needs to get hosed down with flux remover to, well, you know, remove the flux. What I like to do is give it an initial spray and toothbrushing, both sides of course. Then give it a good hose down to remove all the residue, otherwise it turns sticky. And believe me, I hate a sticky residue. Then dry her off. And as long as there's no stick, which there isn't, flux has been removed. Now I just have 6 more boards to do. Just trying not to soak down the motors too much. I'm sure they're rated for this, but still. These boards need to be conformally coated to seal them against a rather hostile moistness of behind a dash. So I am just first masking off the LEDs because the conformal coating, if it gets on the lenses, tends to make them really blurry and dim. Now this coating will also immobilize any moving part once it's dried, so got to mask off the motor shafts as well. Now this stuff has a 2-minute recoat time, and you have to do the coats 90 degrees from each other to get full coverage. Well, after a long wait, the boards for the controllers have finally arrived. See, the problem is that I ordered them the end of March, which is precisely when the world basically shut down due to the COVID-19 pandemic. Because of that, well, they were produced by PCBWay in about 3 days after the order, which was awesome. It took until the beginning of July for them to be shipped to me from China. But for a whopping $5, I got 10 boards, double-sided, with my traditional blue solder mask. And they look pretty damn good. Now that I have my boards and my bags of parts that have been sitting around for a few months, I can get to the assembly. So, what I'm going to do is build the circuit up in stages and then test each stage. I'm going to start with the power supply. Now with my schematic just off camera, these are very small surface mount parts. So the best way to solder them is to use solder paste and a hot air gun. And what I'm doing is I am just placing the paste on the pads where I will place the components. You don't need a ton. And oddly enough, you don't need to even be massively precise, because when you heat it up, surface tension will draw the solder onto the pad and onto the part. Okay, now once the paste is in place, I usually bring the magnifying glass down and I just use my tweezers to try and just break up any that kind of oozed over the IC tracks. And that's just so I can see where to put the chip down, as opposed to having it all blotted out by solder paste. And now I can start placing the components. What I like to do is place like components together, and that way I don't get them mixed up having multiple bags open, because honestly some of these are so small they don't even have part numbers. So if you were to say take a ceramic capacitor and just dump it out on the bench, there's no numbers on it, so it could be anything. Keep it in the bag. Which of course is what she said. Now it's just a matter of placing these components with the aid of the schematic, and finally the Schottky diode. Obviously observing polarity. Yeah, it looks like that's damn near close enough. Time to solder. Well, I have to apologize. I just soldered this, and I thought I hit record on the camera. I didn't. That's okay, there's still plenty of board to go. Now this inductor is kind of a huge thermal mass, and it's big enough that I can just solder it by hand, and it's just a matter of heating up the solder paste and letting it do its thing. One side, the other side's a little tighter. And that's the power supply section. I'm going to fire it up, but a few basic checks. One is, do we have a direct short from ground to positive? No, we do not. That's a good thing. Have the bench power supply set to about 13 volts, and if I very carefully apply that voltage to the vehicle harness connections, if I didn't screw up, we should have 5 volts available at any one of the 5 volt points. Look at that, 4.97. That's damn close enough. And just to verify, we have 12 volts coming in. Well, the power supply works, so the next part of the circuit is the microcontroller. There's 44 pins to solder on the microcontroller. So what I like to do is just put a dab of solder paste at each corner. Then I place the chip. Wow, actually, that was that was basically a perfect drop. Usually I have to nudge it a lot more than this. And then I just tack these corners down with that little bit of solder paste to hold the chip in place. And I have to repeat, that was the perfect drop. That was complete luck. Most of the time, it takes me several minutes of wiggling the thing around to get it in there. And obviously that's what she said. As you can see, I placed some of the processor-related components. Now you'd think that you have to be extremely careful with the solder paste on these tiny pins, but the reality is you don't. And now time to hot air solder it. I'll remember to have the camera on this time. Now I'm going to concentrate my heat on the chip because it's going to take the most, and that should solder everything around it. It's so magical when that happens. Grab this one. Oh, I blew it away. Yeah, sometimes the airflow can be a little too much, and if you don't wiggle in the exact right way, you can blow these really light components away. Grab these guys while I'm over there, and this resistor. Let that side of the board cool down and just hit this resistor right here. Oh my god! Huge solder bridges everywhere! It's a disaster! Now you would think the solder bridges are the end of the world, but they're actually to be expected when hand soldering these things. And easy to correct. So first, you can never have too much flux. Second, just a little bit of solder wick to soak up the excess solder. Oh, and I just inhaled the fumes. And that's all it takes to remove the bridges. And then what I like to do is just touch up each pin with the iron, just to make sure. So yeah, I mean, soldering tiny stuff like this is actually a lot easier than you'd think. And I was amazed the first time that I did it, that I could actually do it. Yep, those look pretty good. Doesn't look like there's any shorts. Everything looks joined. Yep. And we're good. By the way, one of these electronic microscopes, they're like 40 bucks out of China on Alibaba or eBay. Totally worth it. Only a few more components before the microcontroller can be tested. One of those is the 16 megahertz crystal. That's just a matter of heating up the solder paste. by hand. Next part is the 6-pin header. That is the header for the in-circuit serial programmer to program the chip. And I'll tack it in place with a little bit of solder paste on one pin. And go back and solder the rest with some solder wire. And an LED to indicate power and for general blinking. And since I had a few extra pins, then it makes sense to add an LED, use it as like a general OK indicator, a heartbeat, whatever. With the minimal circuitry needed to run the processor on the board, time to test the processor. The traditional way to test a microcontroller is to simply blink the onboard LED. I'm just going to use the standard Arduino blink sketch. The only thing I have to do to it is change the LED built-in variable to pin 5, because that's the pin the LED is connected to. Now this is a bare processor, no fancy Arduino serial port or reset circuitry, so to program it, need a AVR programmer. And that just plugs into the ICSP port, and just make sure the right processor is selected in the Arduino IDE, all the way down at the bottom. That's the Atmel 1284, and I'm using the Mighty Core core. And external 16 megahertz crystal, yep. Brownout detection 2.4, that's fine. That's the 1284 without P. And I use the Bobduino pinout, just because it's basically the same as the Uno pinout, just all the extra pins carry on the pin numbering. And no bootloader. Now, even though I just selected no bootloader there, first I do have to burn a bootloader because it is going to configure the processor for those settings that I just set. Most importantly, 16 megahertz crystal, because if I screw that up, I'll kind of brick the processor. It has to come off the board and reconfigured, and a big pain in the ass. So, burn the bootloader, and holy crap, it worked. That means the processor is running. Reset. And upload the blink sketch. Success! One blinking LED. That proves that the processor is running and it can take a program. And I'll try it at 12 volts, thus testing the onboard power supply. Excellent. Blinking light, stable 5 volts. Now I can build up the CAN controller section. Now this is the 1015T transceiver chip, and pin 1 on this damn thing is identified by a subtle notch on one side of the case. And that's just evil. Some more 0.1 microfarad capacitors, 10K pull-up resistors, one for the chip select line, one for the reset line, 22 picofarad capacitors for the crystal, 8 megahertz crystal in a really dumb form factor with the solder pads on the bottom, and the MCP 2515 CAN controller, which has an appropriate notch at pin 1 like all sane chips should have. I have to start being a little bit careful with the hot air because soldering close to other components now that are already soldered. I don't want to float them away. Now wipe the flux while everything is still warm. Just look it over with the microscope to make sure that there aren't any shorts or grossly wrong pins. Little solder blob. See that little solder blob between the pins there? Doesn't look like it's shorting anything, so should be fine. And now the CAN hardware can be tested. All I've done is lightly modify the code for the CAN loopback test, straight from the examples. All I've done is change the pins to match the Atmel 1284 processor, swap the serial port to serial 1 instead of serial 0, and change the crystal speed to 8 megahertz because I used an 8 megahertz crystal. Well, the fact that it programmed is a good sign. It means that there's nothing grossly wrong with the wiring, and the MCP 2515 is not locking up the SPI bus or anything. So, what I'm doing now is connecting up my serial port, which I will use to supply power to the board, as well as read my serial debug output that is provided by the example code. Just plug that in. Disconnect power momentarily. Open up the serial monitor, and if I'm lucky, when I apply power, aha! Just pull the power for a sec and take a look at the serial output. Excellent! So the CAN hardware works because the chip was initialized successfully, and then after a second, it started sending and receiving data from itself. Perfect! The CAN hardware works. Now I couldn't find a 5-pin connector anywhere, so I just pulled a pin out of a 6-pin connector to fit in my 5-pin header here. In order to test and develop the software that's going to run on this thing, I needed a convenient way to run the MS3 Pro outside of the car, so I built this rig off camera. It basically just consists of an old Megasquirt stimulator connected to an adapter harness that allows it to plug into the MS3 Pro, a little bit of wiring to break out the CANbus connections, as well as supply 12 volts via terminal strip, 2 switches, one to turn on the master 12 volts, another to turn on the ECU, and finally a serial port interface so I can connect it to a computer and Megatune. There's also a short wire harness which will connect to the controller board. Now this is just a serial port so I can view the output of the test code. First, power up the ECU. Tuner Studio is online. And I verify that I can see the simulated ECU sensors by just twiddling the O2 pot a little bit. Now I just have to open up a serial console in order to watch the output of the controller. The Megasquirt is already set to broadcast a whole bunch of values by CAN. So let's power it on. Yes! And that is just a raw stream of all the CAN data coming from the MS3 Pro. What that proves is that everything works so far. We have the CAN line driver chip receiving the raw CAN data, the CAN controller processing that data, sending it over the SPI bus to the Atmel 1284, whose code is then spitting that data back out through the serial port to the computer. Now, all of the 1K dropping resistors for the LCD screens can be dropped into place, and the two tiny MOSFETs, which will switch on and off the LCD backlight. These resistors really want to float around for some reason. It's kind of difficult to not blow them around the board. I may have put too much solder paste on there. Now, just to make sure that all this stuff is soldered properly, I went back off camera and fixed a bunch of the joints. I used way too much solder paste, so a lot of the components started floating away. Oops. Now, just solder on the connectors for the LCD screens. Now I'm whipping up a very quick 8-pin cable to connect the controller to the LCD screen. Just using these Molex connectors to match the ones I used on the board. And a little bit of Cat 5 cable that I had hanging around. Just follow the diagram now and put the terminals into the appropriate position. And that's ready for testing. Once again, for testing, it's just a matter of using the example that comes with the library, in this case the Adafruit TFT library. The only change I've had to make is to change the pin definitions to match my 1284 processor and how I've connected this screen, and set pin 27 high, which will enable the MOSFET and thus enable the blacklight. Blacklight? Backlight. Awesome! Have a working TFT screen. Now it's just going to run through some of the demographics in the library, but the point is that it works. For big things like these capacitors, I just like to stick them on the pads with some solder paste and then heat it up with the soldering iron, because it's a lot of mass to heat up with the hot air gun. It takes forever. Then next, the stepper motor controller modules. And these are just huge through-hole parts, so very easy to solder in. And solder in place. And with the stepper drivers in place, I can just add the connectors. The code I'm going to use to test the stepper motors is the same code that I used back in part 1 of creating this digital dash. The only thing that I've done is I've modified it for 2 motor drivers, and instead of reading from the position of a pot and adjusting the position of the motor, I've just put the motor in the loop. So once the code runs, it should just waggle the motors back and forth. I have the tack stepper here, and I've made a little harness to connect it. Now again, this is just a temporary harness. And because the motor drivers need 12 volts, I have to run it from the power supply. I can't just run it from the computer's USB port like before. So plug in the vehicle harness, and now give it 12 volts. Woohoo! Functioning motor! I'll swap that to the other stepper driver. Power it up. Woohoo! Second functioning motor! Well, that's pretty damn awesome. All the complicated stuff on the board works. Now what remains is all pretty simple. The opto-isolator to detect ignition 12 volts and a few other things. So this optocoupler ended up kind of buried in there, and I don't want to use the hot air gun because I would run the risk of melting the connector and other things beside it. Yep, that works. The remaining parts at the bottom of the board are just a bunch of resistors and filter capacitors to interface with the RGB LEDs, the Nextion panel, and the rotary encoder. So I can just kind of whack these on all at once because, well, there's little chances of this not working. And finally, these 10 microfarad filter capacitors for the screens and I forget what else. Just put that in place, then give it a touch with the soldering iron. Alright, all the electronic components are installed, just need to solder on 4 more connectors, but do that off camera. Then she's done. So the board is now completely finished. Really, the only thing that I have to test is the connector for the rotary encoder, because all the others are just basically straight through connectors to pins on the processor. I also whipped up this quick cable for the rotary encoder, and actually I may use this cable in the final assembly because, well, it's a well-made cable, and the signals to the rotary encoder are not particularly susceptible to noise or anything else, so this cable will work just as well as any other. Well, to test the rotary encoder, surprise, surprise, I'm just using an example that comes with the encoder library. Interestingly enough, I had to modify this library in the interrupt pins file to include the interrupt pin definitions for the Atmel 1284 because it didn't seem to include those. This code being the example is really simple. It just initializes the library. I turn my status LED on pin 5. Set pin 30 as an input because that's the pin I'm using for the button on my rotary encoder. And then it just loops through calling the library and telling me if the position of the encoder has changed. Almost no code because the library takes care of most of it. Just need to program the processor with that code and give it a test. And upload. While this is compiling, I just want to say that you might notice the yellow Visual Studio installer icon down at the bottom of the screen. And that's because every time I seem to want to use Visual Studio 2019, the damn thing wants to update or says it's not installed properly. So then I have to run the update or run through the installer again. Hence, I'm using the stupid Arduino IDE while Visual Studio sits in the background fixing itself. Software as a service, eh? Okay, programmed. I'll just power this up with the serial port. The screen shows that the encoder test is started, so let's twiddle the knob. Excellent. One direction counts down, the other direction counts back up, and if I press the button, woohoo, button pressed. So the rotary encoder works. And you know what that means? Everything on this board actually works. And hey, not to brag, but that ain't too bad for not doing a prototype. So, now I just have to make 2 more. However, before I build the other boards off camera, just gonna clean all of the solder flux off of this one because I don't like leaving that flux on there for too long. It actually absorbs water, can start corrosion, ends up getting under the pins of the chips and just generally can make a mess. So a little bit of flux remover to, well, I don't know, remove the flux. And I'll build the other boards off camera because it's just going to be a production line of 2 more. And through the magic of editing, then there were 3. And now that these are done, we can get to the final assembly, which of course will be next episode. Yep, a 5-parter.